So today I'd like to talk to you about electric circuits. This is our introduction to electric circuits, and we're going to start with a very simple circuit that has a battery and a light bulb connected together with some wire. Something like this. We want to make sure we understand the basics for this simple circuit before we move on to things that are a little more challenging. So we want to start by talking about the battery. Batteries are devices where chemical reactions produce electrical energy. So let's see how this is going to work. We'll take a piece of copper, a piece of zinc, and drop them into some acid. When we do that, you'll notice we get about 0.8 volts being created by our metals. You'll notice that if we put either metal in there individually, we get nothing, but both of them at the same time, we get a little less than 1 volt. The first person to realize that we could create electrical energy from a chemical reaction was Volta in about 1800. This is a great example of what's happening inside a battery. So this is a battery made of zinc and copper like the one I just showed you. And if you could draw it out, we have a piece of zinc and a piece of copper. Some of the zinc atoms are becoming zinc ions and entering the solution. When that happens, they leave behind electrons. That's what this equation is telling us. Some of the zinc metal is turning into zinc ions and leaving behind electrons. Those electrons that are left behind are going to repel each other, so they will populate the entire piece of zinc, making that piece of zinc negatively charged. On the copper, we're going to have hydrogen ions combine together to form hydrogen gas. We'll see little bubbles form on the copper as the hydrogen gas is produced, and it does so by stealing electrons from the copper. Because we stole electrons from the copper is going to take on a positive charge. We now have a positive metal and a negative metal. They're called the terminals of the battery. One's negative, one's positive. It comes from chemical reactions. As we know, negatives repel each other. Positives attract the negatives. So if we hook these two terminals together, electrons will flow through the wire and anything in the wire, like a light bulb, and they'll go to the positive terminal. This flow of electrons is called current. We designate current with the letter I. Capital I stands for current in a mathematical equation. Okay? And again, that current is the flow of electrons from the negative terminal to the positive. We also talk about the voltage of the battery. The voltage measures how much energy these charges are going to get, and we'll be a little more specific as to what we mean by that in just a moment. Okay, but these are two of our key terms, voltage and current. Voltage comes from the chemical reaction. Current refers to the flow of electrons through the wire. Okay, so you might have learned in chemistry these things called standard electrode potentials. What they do is they tell you how much voltage you can get from different chemical reactions under standard conditions. Okay, so you'll notice that reaction involving hydrogen is defined to be 0 volts. The one involving zinc is around 0.8 volts. So together, a zinc copper battery under standard conditions would give us a little less than 1 volt, right around 0.8. Very similar to what we saw when we just saw it on the video. Different reactions will cause different amounts of voltage, but some reactions are reversible. And a reversible chemical reaction means we can undo the reaction, which means we can recharge the battery and use it a second or third or fourth time. Okay, so we have some batteries that are rechargeable because they have reversible reactions, and some batteries that are not. Here are the most common voltages you're going to run across. I'd like you to make this table so that when we're doing things later in this unit, you know how many volts each of these different things will produce, okay? So we have AAA, AA, C, D, 9 volts car batteries, cell phone batteries, and then the outlet that you would plug stuff into. Okay, here's a D battery. It is the biggest of the batteries, and you will see that it is 1.5 volts. That is the biggest of the household batteries. Okay, 1.5 volts. You'll see a cell phone battery, and they will be somewhere around 3.8. More standard, you'll see it listed as 3.7 volts. Either one is fine. Again, depending on the conditions and the concentration of the chemicals, you might get slightly different voltages. All right, but somewhere around 3.7 volts. You'll see a C battery like the one I have here. Mine is leaking chemical, but a C battery is around 1.5 volts. A car battery is around 12 volts. A AA battery, okay, which is this guy right here, he is 1.5 volts. A 9 volt battery, which you might use in your smoke alarms, is 9 volts. And then a AAA, which is the smallest of the household batteries, is around 1.5 volts. You'll notice that all of these household batteries, the AAA, the AA, the C, and the D, are all 1.5 volts. Why are they all the same voltage? Because they all have the same chemical reactions going on inside of them. Why are they different sizes? This one might be used in a flashlight and it will last longer. This one might be used in my remote and it's small enough that I don't have a remote that is giant. Okay? So they have different uses, but they all carry the same voltage because they all carry the same chemical reactions. Your household outlet is 120 volts. And again, take it with a little bit of grain of salt. It may be different depending on the thing you're testing it with, but it should be in the ballpark of 120. Okay, so we have 3 important terms that we kind of touched upon. And let's make sure we go into them in a little bit of detail. Voltage. What does voltage actually mean? Voltage tells you the energy, and this is important, per charge. Okay? The letter Q is used for charge, small q. So it's the energy per charge that we're going to get from our battery. That is measured in joules per coulomb of charge. You might have run across coulombs, I hope you did in chemistry. But if you didn't, coulombs is just a way of talking about how many electrons we've transferred. So 1 coulomb is equivalent to 6.24 quintillion electrons. Okay, lots and lots. Billions, trillions, quadrillion, quintillion. This is off the chart big. So every time 1 coulomb of charge transfers, we're talking about transferring lots and lots and lots of electrons. Okay? So if you have a 9 volt battery, that means that 1 coulomb worth of charge is going to give you 9 joules of energy. You can see that each electron is carrying just a little smidge of energy. Add them all together and you actually start to get something important. 9 joules per coulomb. Our second term is the term current. Current measures how many charges are flowing per second. So current refers to the flow of charges. It goes by the letter I, and it's measured in coulombs per second. 1 coulomb per second means this many electrons per second. Oftentimes, coulombs per second will be called an amp. So if you have a vacuum cleaner that's measured at 11 amps, that means it is having 11 coulombs pass through it in 1 second. Okay? Finally, we have the term power, which we've had many, many times before. We know that power is our energy per second. But there's a real easy way of figuring out power when we're talking about electricity. So when we have our battery Our battery has a certain voltage, maybe like 9 volts. And we're going to have a certain current flowing through our light bulb, maybe 2 amps. So watch how quick this is. You do 9 volts. And remember, volts means joules per coulomb. 2 amps. Remember, amps means coulombs per second. So if we multiply those two together, the coulombs cancel. And you get 9 joules per second, or 9 watts. So to find your power, all you do is you multiply your voltage times your current. PVI, Paul VI. So those are the important terms. Power, energy per second. Current, which is how much charge flows per second. And voltage, which tells us how much energy our charges are going to possess. Remember, voltage does not depend on the size of the battery, but it depends upon the reactions that are taking place inside the battery.